Hello, everyone. This is Shasta Hensley with the Kentucky Department of Education's Office of Special Education and Early. Thank you for joining us as we share the latest edition of our Fall Instructional Strategies webcast series. This webcast is a collaborative effort between the Kentucky Department of Education and the Kentucky Special Education Regional Cooperatives. The team is providing a rich collection of ideas, supports, strategies, and resources. As a disclaimer, many of these resources have been utilized and helpful to other teachers in supporting mathematics instruction. Please note that the KDE or the co-ops do not endorse these products. Let's go ahead and get started.
Hi, everyone. I'm Rebecca Gaddy. I'm a math consultant on the special education team at GREC.
Hi, I'm Savannah Denning. I'm also a special education math consultant at GREC.
Hi, I'm Dwayne Williams, a special education math consultant with GLEC.
Welcome to our session as we explore ways to leverage math tasks to impact student learning. This session is a collaboration of the Kentucky Special Education Cooperatives. Use this QR code or bit.ly to access a digital agenda for this session. In Kentucky, we are always working to increase our impact on student learning in math. But the current context has pushed us to broaden our teaching practices to meet the needs of all students in any setting, including in-person, virtual, or blended and hybrid settings. We are learning to utilize digital tools and strategies to help us accomplish this goal. Today, we're going to provide a brief introduction to the 8 mathematics teaching practices and focus our discussion on a practice that is an effective starting point. In addition, we're going to explore tasks, digital learning tools, and specially designed instruction. Our driving question for this session is, how might we implement tasks that promote reasoning and problem solving for all students in any setting? When we are designing effective math teaching and learning, it's important to consider the instructional core. The components of the instructional core are the teacher, the student, and the content. In Kentucky, our content is clearly outlined in the Kentucky Academic Standards for Mathematics. The content standards provide guidance on what students should know, understand, and be able to do by the end of each grade level. In addition, the 8 standards for mathematical practice describe what students look and sound like while engaging in mathematical learning and reasoning. If we want students to master the practices and the content standards, what teaching practices can increase the likelihood that our students will get there? The National Council of Teachers of Mathematics synthesized decades of research on effective math teaching and learning and developed 8 math teaching practices that drive quality math instruction. All stakeholder groups across Kentucky are working to use this common language to improve math teaching and learning that can ensure mathematical success for every student. As a starting point for teachers in designing instruction, these 8 practices offer specific ideas how teaching mathematics could look and sound. The math teaching practices are not sequential. Instead, they interact with one another to form a framework to guide teacher practice. Starting by establishing math goals to focus learning is essential to a successful learning experience. The next step, which we will focus on today, is to select and implement tasks that promote reasoning and problem solving. You might notice that all other math teaching practices branch off from these first two in order to create a rich learning experience for students. Implementing tasks that promote reasoning and problem solving requires selecting tasks that, first, build and extend current mathematical thinking and understanding, have multiple entry points and pathways to solutions, and engage the student in deep learning. We often think of engaging students by connecting with their interests and passions during instruction, which can be true. However, when we think about task design, we can clarify our thinking by clearly defining what it takes to truly engage a student in a rich learning experience. An engaging experience for students requires that we consider the level of cognitive demand and the engaging qualities of the task. Let's dig into this a little deeper.
Let's explore what we mean by cognitive demand when we talk about math tasks. For our context today, we are thinking about cognitive demand, or sometimes referred to as cognitive load, as the thinking required from students to engage with and progress through a mathematical situation or scenario. Stein, Smith, Henningsen, and Silver in 2000 defined cognitive demand as the kind and level of thinking required of students in order to successfully engage with and solve the task. We have frameworks in education we use to think about cognitive demand, including Bloom's taxonomy and Webb's depth of knowledge. There is a specific tool, however, to think about the cognitive demand specifically in math tasks. It's crucial for teachers to consider the cognitive demand of math tasks as they attempt to implement math teaching practice 2. The goal is to design or implement a task that's at a balanced cognitive demand level, where students are stretched just to the edge of their abilities, yet they aren't frustrated so much that they give up on the task. In this matrix from Smith and Stein in 1998, we see levels of cognitive demand divided into lower and higher categories, with suggestions about what students might be doing at each level. In the lower domain of cognitive demand, students might be working toward memorization, involving skill and drill type activities. They might be working to learn procedures without connection to the underlying reasoning or concept that makes the procedure actually work. An example might be a student learning to add multi-digit numbers where they carry the 1 without truly understanding the place value concept that make carrying or regrouping work. In the higher cognitive demand domain, students are working to understand procedures with connections, utilizing multiple representations to understand the underlying concept behind the process. Students may even be working on math situations where non-algorithmic thinking is required. In this higher demand category, students are able to move flexibly between concrete, semi-concrete, and abstract modes of thinking in order to make sense of problems and find solutions. As we design tasks at the higher cognitive demand level, where students are required to use multiple representations and tools to make their thinking clear, we are also addressing mathematical teaching practice 3. In John Antonetti's 2008 book, Writing as a Measure of Thinking, the author compiled research and first included the 8 engaging qualities in a cube graphic we can use to increase the cognitive engagement of students in the tasks we design. There's a direct connection with Math Teaching Practice 2 and the engaging qualities, particularly personal response and emotional and intellectual safety. Tasks with high levels of engagement and cognitive demand require classroom culture to foster a sense of emotional and intellectual safety, so students feel comfortable taking risk and explaining or justifying their thinking. As students problem solve and use critical thinking to work through math situations, each student may approach the problem in a different way or even come to a different solution. Rich tasks like these, with multiple access points to begin and various possible correct solutions, elicit students' personal response and increase their cognitive engagement. In 2018, Antonetti and Stice wrote Powerful Task Design, where they transformed the engagement cube into a task design rubric. In order to cross the rigor divide, research suggests we must design tasks that push students just to the edge of their comfort levels in the areas of cognitive demand, academic strategy, and cognitive engagement. We want to move students' level of thinking from the lower levels to the higher ones in each of those categories. This task is from Robert Kaplinski's Open Middle Resources. These tasks are open source and free for all teachers to use at their discretion. To explore these tasks and resources, please refer to the link in your handout. The task directions ask students to fill in the blanks with digits to make the answer closer to 200 than 300. This task is labeled as a third grade task and is appropriately aligned to Standard 3 NBT 2 in the Kentucky Standards for Mathematics, which states that students will be able to fluently add and subtract within 1,000 using strategies and algorithms based on place value, properties of operations, and/or the relationship between addition and subtraction. This task is explicitly designed to promote problem solving and mathematical reasoning, which is the foundation of Math Teaching Practice 2. This type of task improves computation practice by moving beyond a traditional algorithm for subtraction. The task provides multiple access points for students and can be solved in a multitude of ways using a variety of computational strategies. The task combines the computational practice with the logic and reasoning of place value, prompting students to think critically about how the placement of digits affects the values in the problem. It is cognitively demanding because students must think critically about how changing the position of the digits changes the value of the overall number. Students make decisions about how to bring their solution closer to 200 by recognizing patterns as they change the position of the digits in the math problem. Additionally, this task is cognitively engaging because there are multiple correct answers, and students can solve in many ways, creating an opportunity for personal response. As students begin to explain or justify their thinking, of emotional and intellectual safety built into their classroom culture, since many different solutions could be correct. In this demonstration, the task is completed with paper number tiles and a dry erase board, creating a task that would be easily implemented in a face-to-face setting. Sometimes it's challenging to translate high-quality problem-solving tasks into digital learning experiences for students. In this video, the same open middle task has been transformed into an interactive slide deck. This type of task is easy for students to access on their personal digital device in face-to-face settings or in hybrid or virtual settings. This task can also be used for independent work or in a collaborative setting by utilizing shared slides or breakout rooms. Students can share evidence of their thinking and reasoning by adding notes to their slide deck or by recording their voice or a video. Regardless of the setting, it's important to provide students time to develop their personal response and foster a culture of emotional and intellectual safety. There are multiple correct solutions to this scenario, providing an opportunity for students to express various methods of problem solving and mathematical reasoning. The cognitive demand of this task requires students to develop a deep understanding of the relationship between place value and computation. This task provides multiple entry points for students who may need extra support, such as scaffolding, explicit instruction, or other specially designed instruction.
Specially designed instruction provides specific supports for students with disabilities. Two examples of SDI that might be helpful in scaffolding this task for students is using concrete tools to make the math visible and explicit instruction. While SDI is specifically for students with disabilities, these strategies may also be useful for other students that need supports. With this activity, we will be using base 10 blocks to solve 405 minus 192. Remember, there are ones, tens, hundreds, and thousands. However, today we are not going to worry about the thousands. Students can use base 10 blocks to complete this Robert Klipinski activity that was demonstrated earlier. Teachers will need to explicitly teach students how to use the base 10 blocks. Since we are working place value, I have added a chart that shows the ones, tens, and 100s place value. In the problem 405 minus 192, I have laid out 405 using 5 ones, 0 tens, and 4 100s. Next, I laid out 192 with 2 ones and 1 100. I begin by subtracting 2 ones from 5 to get 3 ones. To do this, I take the 2 ones and move them to the 5 ones at the top to zero them out, leaving me with 3 ones. I am now left with 3 ones. I cannot take 9 tens from 0 tens, so I must borrow from the 100s place. I substitute 10 tens and remove 1 100s block. Once completed, I begin moving the 9 tens up and removing as I go, leaving me with 1 10. My last move is to subtract 1 100 from 3 100s by moving the 1 100 up to 0 1 100 out. When complete, 405 minus 192 equals 213, which is closer to 200 than 300. While working with base 10 blocks, teachers must connect the conceptual understanding that students are developing back to the abstract of writing the equations along with their answers. Teachers will need to prepare questions to assist students when they don't know where to start or they get stuck while working with the base 10 blocks, to allow the students to move their learning forward rather than being spoon-fed the answers. In hybrid settings, students may be face-to-face setting with their math teacher, and the next day they may be working on their assignments from home. Students with disabilities and struggling students will continue to need their manipulatives to build conceptual understanding that connects back to the abstract learning in mathematics. As a teacher, we need to be able to provide various manipulatives to assist in building that conceptual understanding. In homes, students may not have access to materials to use as manipulatives and may need to use virtual manipulatives to complete their task. There is a link in our agenda that will give you access on using virtual manipulatives. The previous activity can also be done with virtual manipulatives using the base 10 blocks. There are a number of sites that contain a variety of virtual manipulatives. Here are some ways to scaffold support, use explicit instruction, and use math tools to ensure all students have access to this task. Though SDI is specifically developed for students with disabilities, teachers can also use these strategies for any struggling learning to ensure access to high-quality tasks and instruction. Over time, students develop the ability to draw models instead of build models with base 10 blocks, moving within the CSA model. Since Open Middle is a trial and error situation, dry erase boards work wonderfully for this task.
When we revisit our driving question, how might we implement tasks that promote reasoning and problem solving for all students in any setting? We know that tasks that engage students in moving forward in their mathematical thinking will impact student learning. It is important to remember that utilizing concrete tools, digital tools, and providing scaffolds and specially designed instruction are vital to providing equitable access to every student. Thank you for taking time to learn with us today. For more information about selecting tasks that promote reasoning and problem solving for all students in any setting, or for support in designing and delivering specially designed instruction for students with disabilities, contact your local special education cooperative. Happy learning!